Yes, actually, we are studying limits already. This is a material in section 2.2, and then we said we can observe a limit from the graph if the graph is available. Okay, so indeed, this is the example we just finished, example 2.6 on the textbook. And I hope this is a very interesting example because we figured out there is a limit. But anyway, the limit is really not the same as the function value. As I said, the limit really reflects the behavior of the function around that point -1. It may not have anything to do with the actual function value. Actual function value, okay. So limit really reflects the behavior of the function around the point, not necessarily the actual function value at that point. That is the limit. And certainly in this case, it does have a limit. And also, we showed another example. This one more complicated. But anyway, let's just take the graph as given. What we observe here is as x approaching to 0, the function value, because it's a trigonometric function, because of the property of sine, it does oscillate very quickly between -1 and +1. So it's not approaching to any fixed value at all. So really, we are going to say the function, the limit here does not exist. The limit here does not exist. Okay. And also, we did mention, well, sometimes you could have an infinite limit. Limit, it is approaching to infinity. So let's do a little bit more about infinite limits. Okay. So this is the graph. Basically, this is a graph. This kind of graph is a hyperbola. And if you consider the rational function 1 over x, basically the dotted line is being shifted to y-axis exactly. So basically, this is what we can tell. Limit as x approaching to 0 for 1 over x. 1 over x, okay. X, remember there's a little minus sign here. Superscript minus sign, which really means x approaching to 0 from left. And keep in mind, x values are negative. So 1 over x, it is approaching to negative infinity. Negative infinity, or say it precisely, 1 over x, it is getting smaller and smaller. Okay, negative infinity. And also, still let's consider 1 over x, x approaching to 0 plus, which means x approaching to 0 from right. All the x values are positive. Okay, and like 0.1, you are going to get 1 over 0.1, that's 10. 0.01, you are going to get 1 over x, that's 100. And this time it's okay to say 1 over x, it is approaching to, it's getting bigger and bigger. It is approaching to infinity. But the situation here is you consider hyperbola, okay? Consider the hyperbola. And as x approaching to 0, well, let's say this is 0, if we shift the y-axis right here. And from one side, the graph of the function keeps going up. From the other side, the graph keeps going down. So you really don't want to say, sometimes we have an infinite limit, sometimes we have a negative infinite limit. So overall, we are just going to say the limit does not exist. But it does have those two different sided limits. The left sided limit, it is negative infinity. The right sided limit, it is positive infinity. Certainly, many times for positive infinity, we just say it's infinity. Okay. And another, it might be confusing case for beginners. Okay. For it is the same. Well, it is kind of a similar function. 1 over x squared, 1 over x squared, 1 over x, 1 over x squared. But for 1 over x squared, you may want to keep in mind it is always positive. So x approaching to 0 from left, this part of the graph, if you move y-axis to match the dotted line here exactly, as you can tell, x approaching to 0, the graph keeps going up. X approaching to 0 from right, the graph still keeps going up. So indeed, in this case, it really doesn't matter the left limit or right limit. They are just approaching to infinity. And indeed, we are saying the function does have an infinite limit here. Infinite limit. And again, you may want to know, in infinity, it is really not a single number. It is a pattern. It is a pattern. So I'm saying, as I just mentioned, the limit really reflects the pattern of the behavior of the function. When you have infinite limit, which simply means as x approaching to 0 or specific value of a, this type of function, it is getting bigger and bigger. Okay, and so that is, well, still that is a very brief discussion about infinite limits. And indeed, we will look at infinite limits again and again, and also we will consider the other situation, limit at infinity. But anyway, for now, that's all we need to know about infinite limits. Any questions? If you are watching the video, maybe you can take a pause. And for me, I'm just going to continue into the last example about the introduction of limits. As I just said, the limit really only reflects the behavior of a function around a particular point, not necessarily the function value. Okay, so let's take another look. Maybe I'm not sure if this is complicated or not. Anyway, it is still from the textbook. Example 2.11. Okay, the graph is given, and let's take a close look how we understand the limit concept. This is a very good example. As I'm saying, the limit reflects the behavior of the function around that point, not necessarily the behavior of the function. Actual at the actual behavior of the actual value of the function at that fixed point. Okay. So first part for this graph, we are considering the behavior of the function at x equals -4. I say it's fair to make a judgment here. Looking at the graph, I can say the function value at -4. Actually, I need to fix this. So function value at a -4, it is 0 right here. And also as you can tell, as x approaching to this -4 from left, it is approaching to this point, right, which is 0. X approaching to -4 from right, it is approaching to the same point. So indeed, the left limit, right limit, they do match. And in this case, we say the function doesn't have a single limit. Furthermore, in this case, the limit, it does match the function exactly. This is a perfect situation. At x equals -4, you look at the graph. It is a perfect situation. The function value is 0. The limit, it is 0 too. Okay, part A. Part B, we are looking at the situation, the behavior of the function at x equals -2. First, it should be clear, because of empty circle, I don't see any dots, solid dots around here. Okay, so at f of -2, at x equals -2, the function value, it is not defined. And then speaking of limit, I'm checking the behavior of the limit from left. It is pushing everything into this empty circle with the y value equals 3. And from right, still it is pushing everything into this same empty circle with the y value equals 3. So there is a left side limit and the right side limit. And if that is the case, we say there's a single limit, 3. But again, 3 really, it is not a function value. F of -2, simply it is not defined at all. Okay, it does not exist. So that is the behavior of the function at -2. And then maybe look at part C. We are considering the behavior of the function at x equals 1. And then at x equals 1, you want to be a little more careful. When you consider the behavior of the function around this one, you really will have to consider two situations. The behavior of the function to the left of this one, then to the right. I hope you agree with me. To the left, to the right, they look totally different. They are not connected, really. They are not connected. So this is what I observe at x approaching to 1 from left. Okay, trace this part of the curve. It's moving upward, pushing to this solid dot, right? So the left side limit, it is 6. And similarly, the right side, it's getting to the halfway in between, even though it is the empty circle here. But anyway, we are considering the pattern of the function, the behavior pattern. Okay, so it's fair to say as x approaching to 1 from right, everything it is being pushed into this empty circle with the y value 3. So there is a right side limit 3. But the limit from the left and the limit from right, they are not the same. So there's not a single limit. And also, maybe there's another tricky thing here. In this case, even though we do have two dots there, this is the empty circle, this is the solid dot. Okay, solid dot, which really means it is part of the graph. So which really means at function x equals 1, the function, it is 6, but not 3. At x equals 1, you are going to read the function value from the solid dot, 6. Okay. One more trial, part D. We look at the behavior of a function at x equals 3. And still, hopefully, there are two directions, x approaching to 3 from left. The graph keeps going downward, which means it is approaching to negative infinity. Approaching to 3 from right, the graph still keeps going downward. So it is approaching to negative infinity too. Even though infinity, it is not a limit at all. But anyway, overall, somewhat the pattern is consistent. So we still say limit of this function as x approaching to 3, it is approaching to infinity. Clearly, there is not a function value at x equals 3. So I say that f of 3 does not exist. So this is the beginning part of limit section 2.2. There are two ways so far we covered to find our limit. You can find the limit from the graph if there's one. And also, don't forget, the other way to find our limit in this section, it is by doing the numerical calculation. And usually, it would be efficient if you arrange those numerical values in a table, and make a nice table. Hopefully, you can observe if there's a limit or not. Hey, thank you for watching. This is 2.2, Introduction of Limits.